So we're going to take a peek at the quiz preview, go through the problem. You know, if you're flying along on your own, that's fine. We'll end up hitting the answers to everything. So we're just going to kind of take this opportunity to re-talk about some of this, just to make sure we're good to go going into tomorrow. So, all right, factoring. Always want to look first to see if, thank you, to see if we can take something out. But if I can't, and I can't take something out of all three of these, now we go to factoring. Some of you, again, with this, have done the diamond and literally draw it out, and that's fine. But remember, all we're doing here is we're multiplying to get the number on the end. Oh, we got them already. Adding to get the number in the middle. 12 and 2. Anything special with signs? Okay, both negatives. Negative times negative is positive. Negative 2, negative 12, negative 14. All right, knock that guy out. Next one. Do all three terms have anything in common? No. What's that? We could do slide and divide. That's an option. One other thing I'll mention. Whenever you get three terms, if you look at the first and last term, and they're perfect squares, there is a quicker way than slide and divide. We'll take a look at both. What do I square to get 9x squared? 3x. What do I square to get 25? 5. And then to get my sign in the middle, I just steal it from whatever sign's in my middle term. And I'm done. Now, like I said before, though, if catching little patterns like that isn't your thing, can you slide and divide on it? Absolutely. So if I were going to slide and divide, and I'll do it up above here, again, I'd take my original trinomial, and I'd say, okay, let's slide the 9 down. X squared minus 30x, oh, it's going to be a doozy, plus 225. Some of you are like, ooh, I don't like this already. One positive thing about this, though, seeing that it ends in 5 means whatever your common factors are going to be are going to end in 5. So it might be 5, it might be 15, it might be 25, but those are numbers that you can divide in if you're not sure. So in this case, we end up with 15 and 15. And they're both negative because, again, multiply to get a positive, but add to get a negative. But again, don't forget the name of this little method of ours is slide and divide. So we're going to divide each of our negative 15s or minus 15s by 9. What does 15 over 9 reduce to as a fraction? 5/3. So, and since it doesn't come back as a whole number, we just slide that denominator back to the front. In miracle of miracles, we get the same answer. But again, notice how much time and effort I save myself if I take the time to look for the pattern. Then I can just, oh, it's basically the square root of this and the square root of this, and I'm done. But slide and divide, again, will always work. Yep, that absolutely would work. 3x minus 5 squared would absolutely be the same. 3, golden rule first. Do those two terms have anything in common? 4, anything else? X. Got to get them both. So once I get the 4 and the x out of there, what's left to put in the parentheses? Okay, 5x, because 4 times 5 is 20, x times x is x squared, and I've got to have the 1 in there to hold the place. 4 times -1 is -4, and that's all I'm going to be able to do this time. So there isn't going to be some big long process every time. Sometimes it's as simple as taking the greatest common factor out and being done. Bump up a little bit here. What's that? Oh yeah, we're going to get them all. Yeah, I was going to say 5 is, I think, is the one you were saying is your arch nemesis from before, so we're going to take that out too. Okay, 4. Do all 3 of those terms have anything in common? No. So here, if some of you are guessing checkers, you can go for that here, but again, you're going to have lots of combos that are possible. Personally, I think going into slide and divide mode probably is the way to go here. So I need 2 numbers that multiply to -72 but add to -1, so they're going to be close. 2 numbers that multiply to 72 that are only 1 apart from each other. 9 and 8. Multiplying to get the number on the end, adding to get the number in the middle, so what's going to happen with my sign? What's that? Yes. Yeah, -9 and +8, because I want them to add up to -1. So the larger number has to have the negative. Now what? Divide by 6 and reduce the fractions. Over 2, I heard. 4 over 3, because I can divide each of those by 2. But again, since they don't quite simplify down, slide those denominators back to the front. And we've got it. And like I said, if you're a guessing checker, you can do that, but you've got lots of combos that work here. Well, not that work, but 2 and 3, 1 and 6, and then over on 12 you got 1 and 12, 2 and 6, 3 and 4. That can take quite a bit of time, so you're going to want to be cautious if you go that route. But only one of the combinations will work. If you don't mind playing with a possibility of, what was it? 1, 2. Each one would have 2, so if I were to break those up, just to say, 1 and 6, 2 and 3, 1 and 12, 2 and 6, 3 and 4. And with signs, I could flip back and forth on both, so I'd have 6, 12, 24 possible combinations that I could run. So if you hit on the first couple, it's awesome. If not, it can get to be a little bit, but hey, everybody, it's got their own thing with those. Now 5's a different character. It's a shorty. Shorties usually give us a clue. One of 2 things is going to happen. Either I'm going to have a greatest common factor I can take out, or they might both be perfect squares. In this case, they're both perfect squares. So what do I square to get 36x squared? 6x. Square to get 81? 9. And right, since I want a negative or a minus 81, one's negative and one's positive. Order doesn't matter. But that's the type of thing on these that we're looking for. Those short ones, it'll always be one of these 2. Either something to take out or perfect squares where I can break it down right away and get it into its factored form. And finally, number 6. Can I take anything out of all 3 of those? No. So again, guessing checkers, you might like this one because 5 and 1, there's only one option. It's just the second one you're going to have to play with. But, and he's on it already. All right. Let me jot this down here. I went into guess and check mode and got it. Exactly. Because you're like, now how'd they do that quick? Well, think about it for a minute. I've got 5 and 1, because I know that's going to happen for this one every time. I don't have any other choices. So if I try 6 and 3 out, I'm like, oh, 6 and 15, they add up to 21, and play it that way. So in this case, the guess and check may go a little quicker. Because here, if we went back to slide and divide, 90. And then 9. No. What else do we have besides 10 and 9? 10 and 9. We have 45 and 2. 90 and 1. They're like, oh, Harty. 30 and 3. They're like, why aren't any of these working? What the heck? We're getting close. Oh, don't stop on me now. 15 and 6. Ding, ding. We have a winner. Okay, so you'll notice no matter which way we go, whether you're guessing and checking or whether you're doing slide and divide, there is going to be mental math involved. There's no way of avoiding it. This time, though, when I divide by that number that I slid, my first one simplifies. 15 divided by 5 is 3. But the 5 doesn't, so it slides back to the front. You're like, oh, so it is the same we got up here. Yes. But again, it's going to come down to what you're feeling more comfortable with. I can't do one size fits all on you guys, because some of you will flip those in your head, and some of you are like, get me this, and either one's fine. Okay, that's just how factoring works. Then we finally get back into the stuff we've been doing. Sliding things off the page here. Write in radical form, don't simplify. Okay, I get to do the easy part. I'll put the base under your radical. Where's the 1 go and where does the 4 go? 4 goes. Right, the 4 goes on the outside, and I really don't have to put the 1 in there. But if I do, I can put it right next to the 3, or I could even write it like this. But if I just even had what you see right here, that's more than enough. So let's use that as an example to do the next one. Where's the 2 go? Inside, and you can put it right here with, or you could do like we did on the first one, and have 12 through 12 squared. Those are one and the same. I get the same answer either way. So if you put it either way on the quiz tomorrow, I'm perfectly good with that. Exponent form, we just go back the other way. So 6 to the 3/5 or 5/3? Perfect, 3/5 because it's exponent over root. Okay, if you're ever not sure, exponent comes before root in the alphabet. So it needs to go on top, it needs to come first. What about 10? 18 to the 7/4. Life's simple. Again, don't simplify any further, just put it into that form and be done. Like, alright. 11. What do I do to the exponents when I multiply with a like base? Add them. Looking like we need, common denominator here. What's that going to be? 6. 4 over 6. 5 over 6. 9/6. Nice. I didn't even have to ask. I was going to say, here, you've got to reduce that fraction down if you can. Otherwise, it's one of those things where it's just about right, but not quite perfect. So again, if you're adding or subtracting, when you multiply or divide, make sure you've got a common denominator. Speaking of, what am I going to do with the exponents of 12? Subtract. So I've got 3/4 minus 1/6. What's my common denominator this time? Well, I could use 24. I'd have to simplify it. 3/4 into 12ths. 9/12, because 4 times 3 gets me to 12. So 3 times 3 gets me to 9. And 2/12. So I multiply 6 times 2 to get to 12. So 1 times 2 is 2. So it's 7/12. And since the larger exponent's value is in the numerator, I can just leave it that way. If the 3/4 would have been down in the denominator, I'd have 1 over 7 end of the 7/12. Otherwise, it wouldn't have quite been correct. So far, so good. Ooh, 13. What is it? Excellent. How'd you get the cubed? Okay, so 15 over 5, exponent over root. And again, we always want to simplify. And we're set. Again, just keeping life simple. Here comes another one of our nemesis here. Alright, let's chat step functions again. Remember, when you're doing a step function, if you see pluses or minuses, that's all of your different shifts. If you don't, if all you see is a number up front, we're going to treat this just like we would treat slope. So if I don't have any shifts, where's my first dot going to be? 0. Nice big dot there on 0. And then I just follow with slope, and I'll get to the other part in a minute. So I'm going to go down 2 and right 1. Down 2 and right 1. And again, with step functions, typically we like to look at 5. So do I just connect the dots here? I was going to say, oh, please say no. Because this isn't just negative 2x. This is a step function. Okay, it's the greatest integer. So here is where all those little barbells start to come in. And they're really little because this graph is like really small. I guess it's going to be a pen. But again, when you're doing these step functions, it's those little barbell guys. One closed circle where your original dots are and connect it with an open one. Okay? No lines here. No V's here. We're not doing absolute value equations yet on these either. 15. Do I have a shift? Yes. Which way? -3. Which way is that? Left. Okay. I'm like, I can't see that here. So left 3, because it's when it's inside those braces, it's kind of the opposite of what we think, because the format is x minus h. So this is going to be left 3. That's my first point. What's my slope on this one? 1, or 1 over 1. So I go up 1 and right 1. And again, you want 5 steps. And once I get those first dots in there, just making those mini barbells. And then we're done with that one. Okay? Remember, the number in front is a shift. Okay, the number in front is my slope, no shift, excuse me. When I see the pluses and minuses, that's when I'm going to be shifting. If it's outside, that's the up and down one. So, as we flip over here, what's that? Huh? We hate these. Why do we hate these? They're weird. Okay, here's the first thing we're going to notice on our weird graph here. Our lines, hard to spell, lines, both are going to start at x equals 1. Okay, when we had that last quiz, a lot of you were starting your lines at 0 and negative numbers. It's like, no, they have to start here. So when I go to graph my lines, I'm still going to graph them like I normally do. I'm not going to try and get cute. Okay, my y-intercept's still at 2. It's a y-intercept. Don't put it at x. And my slope is -1 over 1. So I go down and right, and I start doing this, but then I take a peek. X is less than or equal to 1. Is that to the left or the right when I'm drawing my line? X is left. So I want it to the left of x equals 1. Well, I'm making all my dots to the right. So how do I get my dots going the other way? What directions do I need to go? Okay. Up and left. Up and left. So I'm like, okay, and it starts at 1. So I don't need these. Is this an open or a closed circle? It's closed because it's or equal to. Make that nice and big. And then from that dot, connect the dots. Because now I'm getting the values of this line that are less than or equal to 1. But that's got to start at 1. I cannot start it, at 0 or someplace else. Same thing happening on the other one. My y-intercept is at -1. And then I'm going up 3 and right 2. Up 3 and right 2. And I stop for a second. Let me make sure I'm doing this right again. X is greater than 1 means I want my line to go to the right of x equals 1. To which some of you are saying, well, wait a minute, we have a problem. I have a dot at x equals 0. I have a dot at 2, but I don't have a dot at 1. What do I do? Perfect. Okay, we're going to draw the line. And when I get to 1, is that going to be open or closed? Open. So when I get to approximately where it's 1, I'm going to make a big open circle. Unfortunately, they're a little smushed here. And then draw my arrow. Because again, I want it starting at 1 and every value to the right of that. And that's how these work. That's your biggest thing. Graph your line, then go back and look to see, okay, do I want the line to the left of this special point or to the right of it? I might even suggest for some of you, before you even start the problem, once you see this x value, I might actually even tell some of you, you may want to put a little dotted line in there just to remind you, that's where my line's got to start. But if I don't, Harty's going to start drawing little pictures on my quiz and be like, what are you doing? Okay, so just graph them normal, find that x value, roll from there. And our other arch nemesis, yes, absolute value inequalities. Now we'd look at this and we'd go, you know what? These shouldn't be that bad. Some of you are going to do this a little bit differently. There's options with all of these. But I'm just going to make some suggestions as we go through these two. This one, absolute value is less than, is an and statement. Okay? And statements are the ones normally that the graphs come together. They're not going opposite of each other. So when I drew these, I rewrite what I see. I add another arrow going the same direction and change the value of, I guess, what we'll call our answer or our solution on the right. Can you write these separately and split them? Yes. Okay? But the reason I do this is going to remind me, oh yeah, this is that one that comes together in the middle. I like having that hint there, which is why I like doing it this way. Work on getting x alone in the middle. There's one last twist I'm trying to throw at you here. What's going to happen in my last step? We have to flip the arrows because I'm dividing by a negative to get x by itself. Tuck it over here. And I almost messed it up. Oh, Harty, that's why you don't use the pen, you silly man. Shows up better on the paper, but not when it all looks like that. Looks like I'm doing some sort of hieroglyphics. Let's see. Here is probably one of those times that going to a decimal is going to help us. Let me try to write this in a little better over here. Okay. There's still a couple of possible pitfalls coming, though. When I go to draw my line, I get my values in. Some of you are going to start looking at this, and you're going to want both of your arrows heading to the right because you're just going to follow what you see. But that's not what's going on here. If we take a look at this for a minute, I'm like, okay, x is less than or equal to 4.25. Less than, heads to the left. Okay, I'm just putting a little arrow on this right now, just to remind myself of what's going on. When I cover this part up, x is greater than or equal to -1. Well, greater than heads to the right. You'll notice my arrows going in opposite directions just end up crashing in the middle. And this should be the easiest interval notation you ever get. Left to right. But some of you, some of you still want to get this going with the ones that go opposite ways. And that's why it's important that these are going to match up. It doesn't necessarily match up with what I see here. You should think 4.25 would come first, but we're always going least to greatest on these. So that's something I have to watch out for. The second one, notice, now the arrow is greater than, okay, my absolute value instead of less than. That's an or statement. Or statements we typically do break up. We leave the first one alone, and then the second one, we flip the arrow and change the sign. But from there, we just solve the little one-steppers that we're dealing with. Again, make sure that your lines are consistent with values in the middle. And now, ors are the ones that do go away from each other. X is greater than 6. Greater. X is less than -2. Less than goes to the left. And this is the one with the big old interval notation, because I have two separate graphs that I'm basically wanting to include within my answer. So here, if I start at the left, I start at -infinity, and work my way up to -2. Parenthesis, just like it is on my graph. U, because I want to connect these, starting up again at 6, and heading off to positive infinity because it goes off to the right. Bless you. And you always want to go left to right. You can't flip these. You don't go right to left, you go left to right, just like you read or anything else like that. So that's my interval notation. Last one. Write the equation that represents the graph absolute value function. Okay, remember, here's my form. I'm going to be plugging values in here, here, and here. Well, how am I going to do that? Because my vertex is my h and my k value, and my slope is the a value. Where is my vertex located for this particular graph? -3, 3. Now, slope, I hate this one with a passion because that dot shouldn't be there. It should be here. So no matter which one I'm counting to, remember, this graph opens up, so is it going to be a positive or negative slope? Positive. The only time it's negative is if it's pointing down. So here, my slope, I go up to and over to. So my slope is just 1. Okay, bless you. And it's not -1. I know it seems that way because I went left, but I also could go up to and right to and get the same thing. So when I go to write my equation now, y equals, my slope is 1. Do I have to have the 1 there? Not necessarily, but we'll just do it to be consistent. X minus -3. But what happens when you minus a negative? Okay, that becomes plus, and then plus my k value. And that's the equation of my absolute value function. You know me well enough at this point. This quiz tomorrow will look eerily similar to this. You've got to go over some of these things. If you start to go over it tonight and you're like, I'm not sure, I will have this. Oh, can I promise 5 o'clock? I'm going to try 5 o'clock. I'm going to try to have this, what we just did, online by 5. So if you need to go back and look at something again, do. Thank you for your cooperation.